in this video, we are going to do an introduction to calculus. We are going to focus on the slope of a secant and the slope of a tangent. What is calculus? Calculus is mathematics of change. It's important because the world around us keeps changing. There are two branches in calculus and from two simple geometric problems. So one is area problems and a curve. So it is regarding the sum and the accumulation. And another problem is from the tangent problem. We are looking for the rate of change as a tangent line, and both of them will describe how fast the object is changing. So the area problem could be solved by integral calculus, and the tangent problem could be solved by differential calculus. So we are going to focus on the tangent problem. We are going to focus on the differential calculus. And in order to find the slope of the tangent, we want to introduce two terms. One is secant, another one is tangent. So the secant is a line that intersects with a curve at 2 points. So this is a blue curve. It's for function y equals f at x. And we pick 2 points, x1, y1, x2, y2. So this is first point, this is second point. We connect them. The green line, we call it the secant line. And if we move the second point closer to the first point, then we will create a line that touches the graph, the curve, by exactly 1 point. So it touches, not intersect with the curve. Okay, and so in order to study the slope of the tangent, we want to start from the slope of a secant. So this is 2 points. We know that is a slope of a line is from the rise over run. And from the 2 points, we are able to find the rise and run. So rise is difference of y. So y2 take away y1. The difference means the subtract, the change. And the run is horizontal difference is x2 take away x1. So this is a slope of a secant line. It's same as our slope for a linear function. Okay, and this is in xy notation. So we also call the slope of the secant is a average rate of change. So it is a change in dependent variable, that is your y value, and divided by change in the x independent variable, that is x. And the change, we could use a symbol delta to represent it. So delta y divided by delta x, and that is y2 minus y1, x2 minus x1. So that is xy notation. And for the function notation, if we use the function f, name is f, input is x, y equals f at x, then the average rate of change in the interval x1 to x2. So it means from x1 to x2, then we want to find the slope between these 2 points on the graph y equals f at x. From the function notation, we need to know how to find the value of the output when input is x1. So we just plug in the x1 to the function notation. Then x2 we just sub in to the function notation. Then we have the y value. Then for the vertical change, it's just f at x2 take away f at x1. So this is y1, this is y2, then over x2 minus x1. So this is for function notation. And the last one is from a graph. If a graph is given, in order to find the average rate of change or the slope of the secant, we just find the 2 points. Read the xy coordinate from the 2 points on the secant line. Then we could use a xy notation, y2 minus y1 over x2 minus x1 to do the calculation. So this is what we have to know for today's. Now we are going to use an example to see how to find the average rate of change, that is a slope of a secant. And in this example 1, it is represented by the average speed. So given function is a displacement of an object. Displacement is the position of an object. H at t equals negative 4.9 t squared plus 30. So the t is the input and h is a function's name. So function h at input t. Determine the average speed. Average speed is a change of the displacement over time. So change of the displacement over time, that is a slope on the graph. So between 1 and 2 seconds, it means we are going to find the slope between the 2 points. So here is a graph for that function. We don't have to use a graph, but it's just let you to see it clearly. So we just want to find those 2 point, the slope between these 2 points. And the first point is 1. The second number, if it wasn't given, we could use a function notation by plugging the t value to find the output, the y value. So t equals 1, we plug in, then we have h at t is h at 1, then replace the t value using the 1. Then we do the calculation. We use the BirdMath. We do the exponent first. We don't have bracket. In the bracket, there's no operation, so we start from square the exponent. So we only do the 1 square. The base is 1, not 4.9. So, well, negative 4.9. Then 1 squared, 1 times 1 is 1. Then plus 30. This one, we do the multiplication, then adding, okay? Multiplication second, then add after that. So negative 4.9 times 1 is negative 4.9, then plus 30 give you 25.1. That is what on the graph. So this is your y value, and the next one, second point is t equals 2. We sub in the t equals 2 to the original function, then negative 4.9, 2 squared plus 30. We do the multiplication exponent first. Negative 4.9 times 4 plus 30. Then do the multiplication. Then plus, it will give you 10.4. Okay, so you have these 2 points. This is x, this is y, this is x, this is y. You could think this is x1, y1, this is x2, y2, and the order, you could use this one as x2, y2, this one x1, y1. It doesn't matter. And after that, average rate of change is just finding the slope. So we are going to use function notations formula h at 2 minus h at 1 over 2 minus 1. So the first number in the numerator and the denominator need to be from the same point. So we sub in the number 10.4, take away 25.1, then divide by 2.1. 2 minus 1 is 1. So we do the calculation, you will find out it's negative 14.7 and meter per second. So this is a slope here, and from left to right is going down, so we know the slope is negative. So this it means that the object is going down, is a down direction. And the next one, we are going to see how we can use this to find this function to find the instantaneous speed, the instantaneous rate of change at point P. So we want to find the tangent line here, the slope of the tangent line. So at when t equals 1. So we want to try it, pick points that got closer to point P and calculate the slope of the secant formed by P and those spots. So we are going to create a table of values. We are going to pick the t value instead of 2. We want to pick 1.1, 1.01, 1.001, so get closer to t equals 1. So we create the table of values here. Then for t equals 1.0, we sub in h at 1. We have the answers from what we have done is 25.1. So it's 25.1. And for the 1.1, we are going to find h1.1. So how to find the h1.1? We are going to sub in 1.1 to the original function. So we are going to have h1.1 equals negative 4.9, then 1.1 squared plus 30. Then we continue to find h1.01, h1.001, and do the same calculation. Use your calculator. I have did the calculation already. So this one is 24.071, and this is 25.00151. This is 25.0902. Then after that, we want to find the slope between the 1.0 and 1.1, 2 points. So delta x, we are going to use this x2 minus x1. 1.1 take away 1.0 give us 0.1. And for the delta y, we are going to use h at 1.1 subtract h at 1. So h at 1.1 take away h at 1. Then continue to fill in this chart. So I did the calculation here. Then this minus this number give you negative 0.09849. This h at 1.001 minus h at 1 give you negative 0.0098. And also we do the calculation, use x value subtract 1.0. So after that, we do the division of these two. So negative 1.029 divided by 0.1 give us negative 10.29. Then do the calculation, do the division. We have negative 9.849. And this one, do the division. We have negative 9.8. So you will see that the slope is getting closer to negative 0.98. Then this means the slope, we move the point from here to t equals 1. The tangent slope is almost equals negative 9.8. Then we call that number is our, therefore, instantaneous speed equals negative 9.8, and that is a displacement divided by time. So displacement unit is meter and the time unit is x. So this is a instantaneous speed. So from this example, we have learned how to do the calculation for the slope of a secant, just using the rise over run, and for the instantaneous speed, we have used pick the point that closer to the point where we want to find the tangent. If it's 1, then we use 1.1, 1.001, 1.001 closer to the 1.0 to do the calculation of the slope. Then we will see that the number is closing to a number. Then we use that number for the approximately instantaneous speed at that point. So the key concept for today is slope of a tangent line. The slope of a tangent line at the point on a curve is the limit of the slope of secant lines. So we find the slope of secant lines, then see the limit, then that we use it as a slope of tangent. In our next couple of lessons, we are going to learn a more accurate method to do the calculation for the slope of tangent. We are going to use limits, and also later we are going to use derivatives. And the learning goals for this lesson is understand that the slope of a tangent is the limiting value of the slope of secant. It's rise over run. And you should be able to find the slope of the secant or a tangent by using xy notation. Is just y2 take away y1 over x2 over x1. That is a slope formula. If it's function notation, then you should know that is f at x2 minus f at x1 over x2 over x1. So this is for function notation, and from a graph, we just read the points from the graph. And after that, use the xy notation to do the calculation for the slope of secant or slope of a tangent. The tangent is just try the point that's closer to the point at the tangent line. So do the delta math homework. If you couldn't access the delta math, you could work on the worksheet, but only the delta math will be marked and will be recorded. So please do the delta math, check your understanding. Thanks for watching.